Hello everyone, I'm Rajasri, Assistant Professor, Department of EEE, working at MLR Institute of Technology, Hyderabad. And today's lecture, I'll be discussing single phase, full wave, controlled rectifier with RL load. So here in single phase, fully controlled rectifier with RL load, we have thyristor 1, 2 and thyristor 3 and 4. We have 4 thyristors. And the basic purpose of a rectifier, it converts AC to DC. That means input has got both positive half cycle as well as negative half cycle since it is alternating in nature. So now during the positive half cycle, the instant when positive half cycle has been appeared, the polarities across the supply will be positive, negative, and because of which positive and negative. Anode of thyristor 1 is positive, cathode will be negative, and since cathode of T2 is more negative with respect to anode, T1 as well as T2 are in the forward bias state. Forward bias state in the sense it is ready to conduct but not at conducting state. If we can provide the triggering pulses for these two thyristors, in that case it starts conducting a current through the load. And that is the reason during the positive half cycle, at this instant called alpha, we can provide the triggering pulse such that T1 and T2 will be coming into the conduction state. So let us see the output voltage waveforms at this instant called alpha, since we are providing the triggering pulse for thyristor 1 as well as 2. See, T1 gets short circuited as well as T2 gets short circuited, whereas T3 and T4 are reverse bias. It acts as off switch, or we can also call it as open circuited. So the moment when we are providing the triggering pulse for thyristor 1 as well as 2, these two are conducting the current through the load right from alpha to pi, during which thyristor 1 and 2 is conducting the current through the load. And let us see the path how the current is actually flowing through the load. Since T1 is forward biased, it is conducting the current through the load through resistive inductive load, again back to thyristor 2, back to supply. This is how the current is actually conducting current through the load. This is the output current. And if you see, supply voltage Vs will be appeared across the load. Since this is positive negative, this is the supply voltage which is actually applied across the load, and now at this instant output voltage is equal to Vs. And if you observe, since T3 and T4 are anyways off switches, T1 and T2 are short circuited, so whatever the supply which we are actually feeding will be appeared across the load, and that is how we get output voltage is equal to Vs. And that is the only reason output voltage is just following the input voltage, that is right from alpha to pi when T1 and T2 is conducting. But here we are making use of an inductive load. That is, when the load is actually conducting current through the load, at that instant, inductor will be charging, because inductor is an energy storage element, and during which the inductor is actually charging. And the moment when it reaches pi, what happens? Negative half cycle appears, and during negative half cycle, T1 and T2 actually need to be turned off because of the negative polarities across the thyristor 1 and 2. Actually, thyristor 1 and 2 need to be turned off. But here we are making use of an inductor, and because of an inductor has a property of it does not allow any sudden changes in the current. According to Lenz's law, by the time the inductor is completely charged, it reverses its polarity. It becomes negative and positive, and it tries to maintain the current flow through the load in the same direction as that of the previous case. So that is how T1 and T2 will be still in conduction even during the negative half cycle of the supply voltage. So that is the reason here, because of the positive polarity which is applied across the anode of the thyristor 2, now T2 and T1 is still conducting a current through the load in the same direction. That is how we are getting the negative spike right from pi to pi plus alpha. Pi to pi plus alpha. That is, whatever the energy stored in the inductor is driving the current through the load. And once it reaches pi plus alpha, whatever the energy stored in the inductor is completely dissipated and it is zero now, because energy is completely exhausted. Thyristor, since negative half cycle is being appeared, the polarities will be reversed across the supply. And so what? Now T1 anode is negative and T2 cathode is positive. That is how T1 as well as T2 will be completely turned off during the negative half cycle of the supply voltage. And because of these polarities, if you observe, anode of T3 is positive with respect to cathode. Similarly, this negative is applied across the cathode. Cathode is more negative with respect to anode. T3 as well as T4 will be forward biased. And at this instant called pi plus alpha, if we can provide the triggering pulse, since T3 and T4 are ready to conduct and we have provided the triggering pulse at this instant called pi plus alpha, T3 as well as T4 are short circuited and it starts conducting a current through the load. So that is how we are getting conduction output voltage right from pi plus alpha to 2 pi because of T3 and T4. And during the negative half cycle, let us see the current path, how it is actually flowing through the load. If you see, when T3 is conducting current through the load, T3, T4 is short circuited, supply voltage this is how it is conducting the current through the load. T3, T4 and back to supply. And that is how we are getting output voltage is equal to Vs when T3 and T4 are short circuited. And that is the reason here output voltage waveform is just similar to that of supply voltage. And again negative spike till 2 pi plus alpha. And at this instant called 2 pi plus alpha, since positive half cycle is repeated, gate triggering pulse is provided for thyristor 1 and 2, and thyristor 1 and 2 starts conducting current through the load right from 2 pi plus alpha to 3 pi. And the cycle repeats. This is the output voltage waveform due to T1 as well as T2. And now coming to the output current of single phase fully controlled rectifier with RL load, this is how it looks like. See, we are making use of a very large value of the inductor in order to illustrate the continuous current conduction mode. Continuous current conduction mode. In order to obtain the continuous current flow through the load, here we are choosing the very large value of the inductor such that we can achieve this continuous current conduction mode. We need to make use of a very large value of the inductor. Similarly, the firing angle value need to be less such that continuous current mode can be achieved. So with this value of the inductor, here current starts flowing. The moment when thyristor conducts, at that instant, see, this is during the positive half cycle, T1 and T2 is conducting right from alpha because current started flowing through the load and it has got inductance which does not allow any sudden changes in the current. That is how inductor current through the inductor is building at a slow rate and it is becoming maximum at this instant called pi. And the moment it reaches pi, what happens? The inductor polarities has changed and inductor is maintaining the current conduction through T1 and T2 even during the negative half cycle. That is how we are getting the current through the load. But since the inductor is supplying the current to the load, inductor itself is driving the current through the load, the current through the load will be getting reduced. As the inductor current is getting reduced, current through the load waveform will also be coming down. And at this instant, what happens? By this time, T1 and T2 is completely turned off, and the moment it reaches pi plus alpha, at this instant, we are providing the triggering pulses for T3 and T4. That is how T3 and T4 is actually conducting the current through the load. And slowly, it is building at a slow rate because of the presence of the inductor. And later, the moment it reaches 2 pi, the current flow is getting reduced because inductor itself is driving the current through the load. Again, current conduction through the load is now because of T1 and T2, and the cycle repeats. And see, we can never expect when the waveform starts and when it ends. So that is the reason here we usually connect it to the back end. So this will be a output current waveform, and this will be a negative spike. So this is your output current with respect to omega t axis. Hope you now understood. If you see, we are getting the unidirectional output because of the flow of the current through the load. During the positive half cycle, current is flowing from A to B. This is the direction of the current which is flowing through the positive half cycle. Even during the negative half cycle, current flow through the load will be one and the same. That is how we are getting positive half cycle as well as negative half cycle converted into DC. And we are achieving unidirectional output. How about voltage waveforms across thyristor 1 and 2? So if you can analyze voltage waveform across thyristor 1 and 2, it is easy to draw voltage waveform across 3 and 4 as well. So let us see the voltage waveform across thyristor 1 and 2. As I told you, whenever thyristor is conducting, the on-state voltage drop across the thyristor will be 0. We will almost consider it as, it will be very less. Since the on-state voltage drop across the thyristor will be very less, it will be almost considered it as 0. And whenever thyristor is off, at that instant, whatever the supply voltage which we are applying will be appeared across the switch. So that is the reason during the off condition, supply voltage will be as it is applied across the thyristor 1 and 2. Because here thyristor 1 and 2 are off, and the moment when we provided the triggering pulse, since thyristor 1 and 2 are on, so at that instant, the on-state voltage drop of these particular thyristors will be almost 0, and it is still conducting further after pi to till pi plus alpha. And if you see here, thyristor 1 and 2 are off, so that is how we are getting the output voltage right from pi plus alpha to 2 pi plus alpha, and it is just following the input voltage waveform. So this is the voltage across thyristor 1 and 2. Let us see V0 average expression. The general expression is 1 by T 0 to T V0 of omega T d omega T. And here, if you see, the time period is, every similar cycle is repeating for pi. So we will consider the total time period as pi, and it is actually conducting from this instant alpha to pi plus alpha. So these will be our limits. It is conducting from 1 by pi total time period, and the limits are actual waveform is present from alpha to pi plus alpha, and this is V0 is equal to, we have Vm sin omega t d omega t, and here Vm constant, bringing it out, Vm by pi, and integration of sin omega t is minus cos omega t within the limits alpha to pi plus alpha. And if you substitute the limits, Vm by pi minus cos pi plus alpha, upper limit minus lower limit, minus of minus we get plus cos alpha, and here cos pi value, since it is minus 1, minus of minus plus 1, we get cos alpha plus cos alpha, that is 2 cos alpha. In that case we get 2 Vm by pi cos alpha. This is the V0 average expression for single phase fully controlled converter. Similarly, V0 RMS expression, we get V0 RMS is equal to, let us see the general formula we have, 1 by T, 0 to T, V0 square of omega T d omega T whole to the power of 1 by 2. And here total time period is, as we have seen previously, 1 by pi. It is actually conducting from alpha to pi plus alpha, where V0 is equal to Vm square sin square omega T d omega T whole to the power of 1 by 2. And here Vm square by pi constant, bringing it out. And in order to integrate sin square omega T, let me write it in this form, 1 minus cos 2 omega T by 2 whole to the power of 1 by 2. We get, I am bringing this constant 2 outside, Vm square by 2 pi, and integration of 1 is omega T, right from alpha to pi plus alpha, minus integration of cos 2 omega T is sin 2 omega T by 2, conducting from alpha to pi plus alpha whole to the power of 1 by 2. Let us apply 1 by 2 for this particular thing. We get Vm by root 2 pi, and applying the limits, upper limit minus lower limit, pi plus alpha minus this, we get it as, substituting the limits, sin 2 pi plus 2 alpha by 2, minus of minus plus, we get sin 2 alpha by 2 whole to the power of 1 by 2. So here Vm by root 2 pi, cancelling out, plus alpha minus alpha, we get pi minus, see here sin 2 pi value is 0. We write it as sin 2 alpha by 2 plus sin 2 alpha by 2, and here minus plus gets cancelled, and this is root pi, and this root pi gets cancelled. In that case, finally we have V0 RMS expression as Vm by root 2. These are the very important formulas. And coming to the peak inverse voltage is Vm here. As I told you, this is the maximum negative voltage which is appeared across the thyristor during the off condition. Similarly, circuit turn-off time. See, circuit turn-off time, it is 2 pi plus alpha minus pi plus alpha. Here, circuit turn-off time, it is given by 2 pi minus, it is off from pi plus alpha by omega. In that case, 2 pi minus pi is pi minus alpha by omega. This is your circuit turn-off time for single phase fully controlled converter with inductive load, that is RL load. And in the coming up lecture, we will be seeing single phase fully controlled rectifier with RL load with freewheeling diode. Thank you.